from the EL6303 probability class. Today I am going to explain a lecture on matched filters. So let us consider a system or a signal f of t. So it gives rise to the output a or minus a. So both a and minus a have the same probability and they travel in the same time period t0. So this is the given function of a. So this so it's from 0 to t and the function is f of t. So this is capital A, and the same thing which is inverse gives rise to the negative a. So by applying a noise signal into the system, we get graphs such as this, and in the negative axis we get a graph such as this. So here is the block diagram of the function. So the given system, the given signal is passed through a transmitter. The transmitter's output is given as f of t. Then it is passed through a noisy channel. The noisy channel is given by v of t. So once the transmitted signal and the noisy signal get clubbed together, we get the output, that is x of t. So we can determine this in two ways. The first approach is, so let us consider a specific time region, like let's take a point t0 over here such that it's between 0 and t. So the point t0 is taken, so it's 0 less than t0 less than t, but in the case of x of t0 is greater than 0. So once in this method the signal x of t is passed through a synchronized sampling, and then the output is passed through a threshold device, and if the output is greater than 0 we get a value of plus a, and if the output is less than 0 we get a value of minus a. Now proceeding to the second approach. Now let us compare the area of the data with 0 at t equal to t. So the signal at t equal to t is given by this. Here the normal signal and the noise signal are mixed together, and it gives rise to the value plus a. And here the normal signal and the noise signal are mixed together, which gives rise to the value minus a. So here is the block diagram of the receiver. Here the input signal x of t is passed through an integrator. The output signal through the integrator is given by y of t. So the y of t signal is then passed through a synchronized sampling given by t equal to t, and the output is passed through a threshold device. Here the output of the threshold device, if it is greater than 0 gives rise to the value plus a, and if it's less than 0 gives rise to the value minus a. So here the value of the integrator is given by y of t equal to integral t to t minus t to t x of alpha d alpha. The given system y of t equal to integral t minus t to t x of alpha d alpha is an LTI system. So the LTI system is given by h of t. So the h of t equal to y of t at given x of t equal to del of t. So upon expanding this formula we get integral t minus t to t del of alpha d alpha. So we can also rewrite this equation as integral minus infinity to t del of alpha d alpha minus integral minus infinity to t minus t del of alpha d alpha. Here L of t equal to u of t, where L of t is the impulse response and u of t is the unit step function. So which is given by L of t minus L of t minus t. Here both L of t and L of t minus t are of the same shape, but L of t minus t is just time shifted. So the final output of the receiver end is given by the transmitter, which gives rise to a signal f of t. Now the signal f of t is passed through a noisy channel v of t. So the output of f of t plus v of t, here it's f of t plus v of t, that is x of t, is then passed through a LTI system, that is h of t equal to L of t minus L of t minus t. Then the output from the LTI system y of t is then passed through a synchronized sampling with t equal to t, which is then passed to a threshold device. The output of the threshold device, if it is greater than 0 gives rise to the value a, and if it is less than 0 gives rise to the value minus a. Let's proceed with the discussions. First, the impulse response of the filter h of t is given by L of t minus L of t minus t. So this can be written as k into f of t. So h of t equal to k into f conjugate of t naught minus t if f of t is complex. So when f of t is complex, we can write h of t equal to k into f conjugate of t naught minus t. So the second discussion is, by using the filter h of t equal to L of t minus L of t minus t, we get the signal to noise ratio, SNR, signal to noise ratio. Equal to the square root of power of signal at some t naught by power of noise at some t naught, which is given by square root of signal squared by square root of the mean of the noise squared. Both signal and noise are taken at the time t equal to t naught. The next we proceed with the general problem of a matched filter. Here we know that the output signal x of t equal to the input signal f of t plus the noise v of t. So we know f of t is known, and v of t is a regular WSS process. WSS means Wheatstone stationary process with a known power spectrum SV of omega. Here the conditions of widespread spectrum is the mean of the system should be 0, that is E of V of t equal to a constant, and the auto correlation RV of t1 comma t2 equal to E of Vt1 into Vt2 equal to RV of t1 minus t2 equal to RV of tau, that is equal to the time difference, that is RV of tau. So upon applying Fourier transform to RV of tau, we get the power spectrum SV of omega. Here the effectiveness of detection depends on the ratio R between f of t naught or f of t of certain time and square root of the second moment of noise. Here R is equal to the modulus of f of t naught by the square root of E of V squared of t, that is the mean of V squared of t. Here the common method for increasing R involves linear processing of data. So the given signal x of t, which is a combination of the input and the noise signal f of t plus v of t, when it is passed through an LTI system, that is h of t, when taken a Fourier transform gives rise to h of w, and the output y of tau equal to yf of t plus yv of t. So this proof can be claimed by two reasons. So this is the claim 1. Here if v of t is white noise with the power spectrum SV of w equal to S naught, that is a constant. So the h of w equal to k f conjugate of omega e power minus j omega t naught. Here the impulse response h of t is given by k f conjugate of t naught minus t, so which is given by k into f of t naught minus t if f of t is real. So the signal to noise ratio SNR is given by square root of integral minus infinity to infinity modulus of f of omega the whole square d omega by 2 pi s naught. Now let's proceed to squash inequality. Squash inequality states that the modulus of integral f of x g of x dx the whole square less than or equal to integral modulus of f of x the whole square dx into integral modulus of g of x the whole square dx if f of x is equals to k g conjugate of x. So we are going to prove this equation. So which is given by the proof. Now let us take a quadratic equation as an example. Az squared plus bz plus c equal to 0. So we can convert this equation into this form, which is given by modulus integral f of x g of x dx less than or equal to integral modulus of f of x into modulus of g of x dx. So this is given by this equation, b squared is less than or equal to 4ac, which is given by the roots of the quadratic equation. So this in turn gives rise to integral z modulus of f of x g of x the whole square dx is equals to, now we are expanding this in the formula a plus b the whole square dx. So a squared plus 2ab plus b squared. So z squared integral modulus f of x the whole square dx plus 2z integral modulus f of x g of x dx plus integral modulus g of x the whole square dx. So all these are greater than 0. Now further simplifying this, we get 2 integral z modulus f of x modulus g of x dx the whole square is less than or equal to 4 integral f of x the whole square dx into integral g of x the whole square dx. Here let's proceed with the proof of claim 1. Here r squared is equals to the modulus of yf of t naught the whole square by the mean value of yv squared of t. So which in turn implies modulus of 1 by 2 pi minus infinity to infinity yf of omega e power j omega t naught into d omega the whole square by 1 by 2 pi minus infinity to infinity s yv of omega d omega. This is the power spectrum of v. So this is given by modulus minus infinity to infinity yf of omega e power j omega t naught d omega the whole squared equal to modulus of minus infinity to infinity h of omega f of omega e power j omega t naught into d omega the modulus squared, which is less than or equal to integral minus infinity to infinity modulus of h of omega the whole squared d omega into integral minus infinity to infinity modulus of f of omega into e power j omega t naught the whole square d omega. So this can be rewritten as integral minus infinity to infinity modulus of h of omega the whole square d omega into integral minus infinity to infinity modulus of f of omega the whole square d omega. So this is given by integral minus infinity to infinity s yv of omega d omega, which is equal to the integral minus infinity to infinity sv of omega into modulus of h of omega the whole square d omega, which in turn implies s naught integral minus infinity to infinity h of omega the whole square d omega. So this is the block diagram. Here v of t and the power spectrum sv of omega is passed through LTI system h of t on Fourier transform gives us to h of omega. The output is yv of t. Here power spectrum syv of omega equal to modulus of h of omega the whole square into sv of omega. Now coming over here, the r squared is less than or equal to 1 by 2 pi the whole squared integral minus infinity to infinity modulus of h of omega the whole squared d omega integral minus infinity to infinity modulus of f of omega the whole squared d omega, the total divided by 1 by 2 pi s naught, this is s, it's not an integral, integral minus infinity to infinity modulus of h of omega the whole squared d omega. This in turn can be rewritten as integral minus infinity to infinity modulus of f of omega the whole square d omega by 2 pi s naught. The impulse response h of w is equal to k into f of omega e power j omega t naught the whole conjugate equal to k f conjugate of omega e power minus j omega t naught. Here r is maximum if h of omega equal to kf conjugate of omega e power minus j omega t naught. The inverse fast Fourier transform of f conjugate of omega e power minus j omega t naught is given by f conjugate of t naught minus t. Now let's proceed to claim 2. Claim 2 states that if v of t is WSS with sv of omega, that is the power spectrum of v, the system function of a match filter is defined by h of omega equal to k f conjugate of omega by sv of omega into e power minus j omega t naught. The signal to noise ratio r is given by root over 1 by 2 pi integral minus infinity to infinity modulus of f of omega the whole squared by sv of omega d omega. So now let us prove this. We know the signal x of t equal to f of t plus x plus v of t. So this is the combination of the input signal and the noise signal. So now it is passed through a whitening filter of v of t. And the output is given by x1 of t equal to f1 of t plus iv of t. Now it is the iv of t is the white noise with siv of omega equal to 1. Now this input is passed through a LTI system h1 of omega and the output is given by y of t equal to yf of t plus yv of t. The whitening filter of omega is given by siv of omega, which in turn is given by sv of omega into modulus of fv of omega the whole square, which is equal to 1. Therefore sv of omega equal to 1 by modulus of whitening filter of omega the whole square. Now h of omega is given by the whitening filter of omega into h1 of omega equal to whitening filter of omega into k into f1 conjugate of omega e power minus j omega t naught. The whitening filter of omega into k into f conjugate of omega into the whitening filter conjugate of omega e power minus j omega t naught, which in turn is given by k f conjugate of omega to whitening filter of omega the whole square into e power minus j omega t naught equal to k into f conjugate of omega by sv of omega e power minus j omega t naught. So this we have proved for claim 2. From claim 1 we get r equal to root over 1 by 2 pi s naught integral minus infinity to infinity modulus of f1 of omega the whole square d omega, which is given by 1 by 2 pi integral minus infinity to infinity modulus of f of omega into widening filter of omega the whole square d omega. Here s naught is equal to 1. S naught is equal to 1. So root over 1 by 2 pi minus infinity to infinity modulus of f of omega the whole square into widening filter of omega the whole square d omega, which is given by root over 1 by 2 pi minus infinity to infinity modulus of f of omega the whole square into 1 by sv of omega d omega. Thus proved. Thank you.